Hello everybody, my name is Covey.
Hi, my name is Katie.
Hi, my name is Kat. And welcome to
The Couch Potato Lab,
where we bring the science to the comfort of your own homes. Today's episode is going to be an electrifying one, hey? Oh, look at me go. Look at this. Look at this.
Wow, Kobe. Wow.
So electrifying, let me tell ya. Make sure to download the lab manual from bit.ly/couchpotatolab and has all the information about today's episode. If you have any questions during today's episode, make sure to text in your questions at 306-570-1013. If texting isn't your fancy, you can reach us through our social media at Eyes Youth. And if you're going to use any of these social medias and asking a question, make sure to use that hashtag CouchPotatoLab so we can find your questions. Thank you so much. Today's episode, again, is electrifying, and I brought in two of my favorite scientists in the entire world. To my left, who do we have?
Hello, everybody. My name is Katie. My pronouns are she, her. And my fun fact for today, I think this is a very relevant fun fact, is that I'm terrified of balloons, and you probably already know that from previous episodes, but I really want to reiterate that it is very tough for me to be here today. You will see with all of our experiments with all these balloons that I am going to be here working through it all, but that's okay because I'm here and I'm excited to be on the Couch Potato Lab with you guys today.
Nice, Katie. Maybe if you're, since you're afraid of balloons and like I'm making that, remember that like balloon game for your birthday?
Oh yes.
Maybe we'll tone it down a little, or just for you.
I think that'd be
yeah.
cool.
Okay. Hello everybody. My name is Kobe. I'm today's host. My pronouns are he, him. And yesterday I went back in time and saw some dinosaurs, and it was wow, what it was an adventure. And I brought in some cool things that we're going to show you later on, but I learned the power of magic. And I'm going to show you all about that later on. But before we do that, let's introduce our next scientist to my right.
Hello, my name is Kat. My pronouns are she, her, and my fun fact for the day is that I've actually been plotting against Katie. All these Couch Potato Lab episodes, and we've been practicing exposure therapy on her. So by constantly having her have to be in these episodes with balloons, we've been hoping that she will conquer her fear of balloons.
Well, Kat, I really appreciate that from one friend to another. I appreciate what you've been doing for me, and today is the big test, so we'll see how that goes. So before we start the episode, we did want to acknowledge that we are coming to you from Treaty 4 territory, which is the traditional territory of the Nayawak, Nakaway, Dakota, Nakota, and Lakota peoples, as well as the traditional homeland of the Métis-Michif Nation. We also wanted to recognize that you may be watching this live stream from other numbered treaties or from unceded territory. So thank you for taking a moment to recognize this with us.
Thank you, Katie. I am a magician. Let me tell you, I'm an amateur magician, and I'm kind of like running out of ideas. My repertoire is like not so great. Like, I can play with fire and it's great. And here's a little video of how I'm so talented with fire.
Wow.
Wow, look at me go.
Wow, you must be pulling in the big bucks for that magic trick.
Yeah, but that's the thing is like that's the only thing I can do. And I just like I need to entertain my guests and all these spectators. And I'm just running out of ideas. Can you all help me? Like, what can I do?
Yeah, Kobe, I think that people are going to get really bored if they just watch that the whole time. And I know that you have that big, like, magic show coming up, right? And so you should probably learn a few new tricks. I think we could maybe help him out, Kat.
I mean, fire is very exciting. It does have that je ne sais quoi that keeps people coming back. But Katie and I have our own tricks up our sleeves. But these tricks involve science. So here I have this balloon. As you can see,
Katie's favorite thing in the entire world.
There are no strings around this balloon. Now, I'm going to rub this balloon on my shirt, and I have some little small pieces of tissue paper here, and just watch what happens with these pieces of tissue paper when I bring my balloon by them. All right. Are we ready?
I'm ready. Whoa.
Wow,
They're
Kat.
flying up and they're sticking.
Wow. See, and that was pretty small scale, because here's another tip, Kobe. When you're doing a show, you want to start small and get bigger and more grand with your tricks, right? So now I'm going to bring out the big mother butterfly here. And now, same thing. Watch what happens with my beautiful butterfly when I bring my special balloon by it.
Dun, dun, dun,
Ready?
dun, dun, dun. Yes. Wow, it's flapping its wings.
Yes, my butterfly is flying, and I'd like to say that I am so proud of Katie for sticking out through the work with the balloons.
Oh, I'm just sitting here watching, and I am not plugging my ears at all. So,
yeah, you watched the entire thing, hey?
Yep.
All right, thank you, Kat. That was really cool. Maybe I'll add that kind of little trick to my magic repertoire. Katie, can you help me out with another one?
I most definitely can. So, Kat, did a really cool magic trick, but we don't know. Kat's a little bit of a sneaky, and maybe she has like a magic shirt or something. So I wanted to go ahead and show everybody that it's not just Kat, that I can also do some magic, and we can also teach Kobe some of this magic.
Ooh.
So I'm going to go ahead, and I have a few things here. I have a plate, some salt, and some pepper. And no, I am not going to be using that to eat my lunch. I'm actually going to be showing some magic here. So you can also follow along if you want. All you need are these 3 ingredients and then a balloon or a comb. And what we're going to do is I'm going to go ahead and I'm going to pour some of this salt onto this plate here. And you want maybe about that much, just so that you can have enough on the plate. So I'm going to go and I'm going to spread out this salt here so that we kind of want a nice even layer on the plate.
That's how much salt I dip my my French fries in. Is that okay?
Oh, Kat, we're gonna have to talk about that a little later. So we have all our salt here, and so now what we're gonna do is we're gonna go ahead and we're gonna add some pepper. And if you're doing this along at home, you want to add maybe about a teaspoon of pepper. And with this, you want to make sure that you kind of have the peppers kind of spread out throughout the salt, so you don't want it all kind of in one clump.
Oh, Katie, that happens to me all the time. When I get ready to make my lasagna or something like that, I always have my salt and pepper ready to go, but sometimes I mix it together and I'm like, no, the salt has to go first, and then I can add the pepper when it's, when the salt all dissolves and stuff like that.
Well, Kobe, do you ever have any issues with trying to get this apart? Sometimes if I accidentally add some pepper or something and I don't really want this. Say if I only want the salt, do you two believe me if I say I would be able to separate this pepper from the salt?
What? I don't think so.
Maybe in 20 years, you'd see it again and it'd be separated.
Pick each one up with a tweezer.
Yeah.
Oh, you two just don't believe in me. Well, let's go and show them. So, Kobe,
Yes.
if you want to look under your desk, I have put a comb under there. So I want you to find that comb, and I
Wow.
want you to rub it against your hair. And I want you to do that just for a little while.
Oh, you're back, Kobe. You're teasing. This is not the 80s.
So go ahead and give that a nice little
Ooh, my hair's tangled.
nice little shake.
Your hair's tangled.
You know what? Kat and I were joking that by the end of the show,
You
he's
know
gonna
what?
be bald.
Katie told you this was for the experiment, but we actually just thought your hair needed a good combing.
Yeah.
Oh, okay.
Oh, okay, Kobe. I think that should be good.
That's
so
good?
go ahead and you can pass it to me. I'm gonna grab the handle. Now watch what happens when I put the comb near the salt and the pepper.
I don't see much happening.
All right, so there's not too much happening when I do that. If I look really closely, there's a few kind of strands kind of picking up, but we know that maybe that means the comb is not the answer to what we need to do for this experiment. So, Kobe,
Yes.
if you want to go ahead and look under your desk again, I have put a balloon under
Oh my
that.
god, so many magic tricks today. Wow, I found it. Hey.
And I want you to go and gently rub it on your hair.
Gently, I'm gonna do the opposite.
Okay.
Yeah?
Yeah, you go a little bit more.
Good?
Okay, that's good. Now you can pass it to me. And I'm going to go ahead and do this again.
Wow. Look at all the pepper
Oh my
that's
god,
picked
that's
up.
a lot of pepper.
You see that? Do you see how it's actually picking up?
Ooh, I can hear the
Wow.
sounds.
And you can see that I actually have pepper on my balloon, and it's only pepper. I don't have any of the salt on my balloon. So,
Oh, nice separation.
you both underestimated me, but I'm
Yes.
actually able to separate this pepper from the salt. Because go ahead, you can look. It's only pepper on my balloon.
Yeah.
Just
You know what?
pepper.
I'm sorry I doubted you, Katie. Next time I will estimate you.
Yes.
Estimate you?
Exactly.
Overestimate.
Well, I think it's important to maybe let Kobe know our little secret, and that, yes, I guess this is magic, but it's also science. So what Kat and I are doing is we are using principles of science to do these demonstrations. And we need to know a little bit of the background story before we continue with the episode. So, everything is composed of atoms. Everything in the world is made up of very, very, very small little units that make us up, the world around us up. And these atoms have both positive and negative charges. So little components that are part of these atoms, some of them are called protons, and protons are positively charged, and some of them are called electrons, and electrons are negatively charged. So what happens is when we are looking at something called static electricity, which I'm sure you have heard of before, that happens when electrons are transferring from one object to another. So if something is negatively charged, it has a buildup of electrons on it, many, many electrons. And what happens is that when it approaches something with a positive charge, then the electrons are going to jump from that one object to the other object. But the cool thing is that they don't have to be touching. So that is where static electricity comes from. So when one thing is negatively charged and another thing is not that negatively charged, as soon as we get close to something, electrons are going to jump from one object to another without even touching it. So it's really about the unbalanced charge of two objects that are interacting. And so Kat and I have been using static electricity to do all of these tricks. So that is really our secret here, Kobe, but it does look like magic.
You may say that maybe opposites attract. Hey, positive and negative, they come together and a reaction occurs.
Exactly, Kobe.
Wow.
Opposites attract, and that's exactly what happened when I was doing my salt and pepper experiment. So the balloon and the comb both had a negative charge, but the pepper had a more positive charge. So what happens is when we held the comb or the balloon over the pepper with the more positively charged and the balloon with the more negatively charged, the pepper actually jumped up to the balloon. Now the salt is a bigger molecule, and also it doesn't have that positive charge as much as the pepper, and so it doesn't jump up as fast as the pepper. So it's about the different components that we were using and the different charges, and that's why the pepper jumped up but not the salt.
That makes sense. How about you, Kat? How does that work with your tissue paper?
So with my tissue paper, when I was rubbing that balloon on my shirt, I was passing electrons from me to the balloon. So when I brought that balloon near the tissue paper had a positive charge, and so the electrons jumped from the tissue paper to the balloon and the butterfly, attracting them together.
Oh, that makes sense. Thank you. All right, now I know some science about behind all of this. I can include some static electricity demonstrations with my magic repertoire. And if you have any questions during the episode, make sure to text in your questions at 306-570-1013. Of course, we are at all our social medias at Eyes Youth, so like Facebook, Twitter, and Instagram. Make sure to use that hashtag Couch Potato Lab so we can find your questions. Those are the two ways to contact us, and it's going to be great. Now that we learned a little bit about positive and negative charges, it kind of brings me back to when I learned about something in high school. And I am a visual learner. I learned I want to see how things are organized visually, and many scientists are as well. And Niels Bohr proposed the Bohr Model, and this kind of shows how electrons are placed around atoms and how protons and electrons and neutrons all occur. And what happens is that protons and neutrons are really, really heavy, so they are pretty much at the center. They are the nucleus of an atom, and atoms are are everywhere, right? They make up the matter in our world, and electrons are the things that are floating around the nucleus. So again, nucleus has the protons and the neutrons, and the electrons will be floating around it. And this is kind of what the Bohr model depicts as well. Right here we have the Bohr model, and it shows that these electrons are actually orbiting the nucleus. And what I mean by that is, maybe picture how planets orbit the sun, right? They are moving around the nucleus. And let's do a little example right here. I have sodium. Sodium is a element on the periodic table, and it's represented by Na. And the atomic number for sodium is 11. What that means is that sodium has 11 protons and 11 electrons. And these electrons will be around these circles around the nucleus. And this is where the electrons will be on. So let's take a look at sodium right here again. Sodium has 11 electrons, and the first shell can only have 2 electrons. That is the maximum amount of electrons it can have. So I'm going to draw electrons and represent it by this yellow circle. So that's 2. 11 minus 2 is 9. So we need about 9 more. Am I right? Yeah. Okay. 11 minus 2 is 9. Great. Now we have to show 9 more electrons. Now let's quickly write that. The next orbits or shells can only have a maximum number of 8 electrons. So let's put 8 right here. Alright, right, now we have 10. We have 10 electrons on sodium, but we need one more, so we have to add another shell. There you go. So that one last electron can be on that shell. And how to differentiate between these shells is there's valence electrons and core electrons. Valence electrons are the ones on electrons on outside or the outer shell, and all the core electrons will be the inner shells. So the 10 electrons are the core electrons, and then the last 11th electron is the valence electron because it is on the outside shell. Now let's take chloride, for example. Let's do another example, and I chose to do chloride, and it has 17 electrons in total. Why? Because chloride has an atomic number of 17. All right, let's draw these electrons on these shells. Remember, the first shell, the most inner one, can only hold a maximum of 2 electrons. So let's draw that. All right, Katie, can you remind me, on the next shell, what is the maximum number of electrons it can hold?
Okay, I remember that it is 8.
Correct.
So it's the first shell that can contain 2 electrons, but all other shells after that can only have a maximum of 8 electrons.
Perfect. There we have it. All right, we got 10 right there. Let's draw another 8. Oh, I just need 7 more.
So, Colby, I'm kind of looking at these diagrams, and I'm just wondering, because, sodium, it looks like it has kind of one random one in its outer shell, and chloride, it looks like it is missing a partner. So, is that right? Is that what it's supposed to look like?
Yes, that is how it's supposed to look like. And the thing is, atoms sometimes they really want full sets of shells. And what is the fastest way for sodium to get a complete shell, right? It has only one valence electron. What do you think should happen here, Kat? What's the fastest way for sodium to get a full shell?
I think that the fastest way for sodium to get a full shell is maybe would it just steal one from the chloride?
I think, close, you're really close.
Oh, wait. I think they could be really good sharers. I think that they could practice their sharing and share their outer shell ones that are missing an extra electron.
Yeah, atoms can do that, very, very true. But I think in this scenario, since because sodium wants to have like complete shells, the fastest way would be to lose that electron right here. If they lose that electron, then the next shell is already complete. Chloride, on the other hand, needs one more to have a full, complete shell. So, if that's the case, sodium can actually give chloride its electron. So then sodium has a full shell, and chloride has a full shell. So that's how atoms work when they bond together. And I think we can do another demonstration on how these bonds work. Hey, Katie?
Yeah, I think that we could. So I brought some of my dessert here because, Kat and I have a very special friendship. She helped me with my balloon therapy, and so I thought it would be nice of me to share some of my Smarties with her. So we can see on Kovi's desk that I have a whole bunch of Smarties, and what we're going to do is Kat and I are going to go ahead and we're going to negotiate, and we're also going to learn about some different kinds of bonds that can happen between atoms at the same time. So the first bond we are going to show is a covalent bond. So there's kind of 2 clumps on Kovi's desk. The one that is closer to me is mine, so the orange, pink, yellow, red, and the one that is closer to Kat is hers, so the blue and the brown and the yellow. So you know what, Kat? I'm kind of looking at my Smarties, and I can see I have 2 Smarties in the middle, and then I have 7 around the outside. And Kat, I'm kind of looking at yours, and you have the same, and my shell is looking a little bit empty, and I was just kind of wondering if you would maybe want to share some with me?
I think I would like to, because also you have the pink Smarties, and I really like the pink Smarties, and maybe I could share a blue Smartie with you. Do you think we could try that?
Yeah, let's go ahead and try that.
Yes, if we can like come together, what they can do is they can share this yellow Smartie together and form a bond.
So this is modeling what is called a covalent bond. So Kat and I both wanted each other's Smarties. We really like the colors of each other. But, you know, I'm feeling pretty nice to Kat and she's feeling pretty nice to me. We want to share our Smarties. So that's what happens in covalent bonds, is two of the atoms, they will actually share their electrons. They're not going to take one from one another, but they're actually going to share the number of electrons. And when they do that, they're kind of bound together. They can't just separate based on that. How does that sound, Kobe?
That sounds great. And that was covalent bond. What's another bond that we can talk about, Katie?
So, you know, let's say that I kind of have a personality switch and I'm not really looking at sharing with Kat. And, you know, I'm just really annoyed because Kat has more Smarties than me. And I was the one that brought the Smarties for her. And she's taking all these Smarties and I still have an empty shell. And she has a full shell plus extra. And Kat, I really want you to give me one of these Smarties.
Well, lucky for you, Katie, that I am in the giving mood. So I will graciously grant you one of my Smarties so that you can fill up your own shell.
Nice. All right. So if you take a look at Cat Smarties right here, 1, 2, 3, 4, 5, 6, 7, 8, 9. She has a total of 9 shells. This can be represented by like the valence electrons. And Katie, on the other hand, has 1, 2, 3, 4, 5, 6, 7. 7. And remember, orbits can only have a maximum of 8. So what we can do, right, since Kat is being in a very giving and generous mood, she can actually donate one of her Smarties and give it to the greedy Katie over there. And bam, look at that. They have 8 electrons around their core electron.
Well, you know, I'm feeling much better now because I have a full shell and I feel like that's kind of fair now. What do you think, Kat?
Yeah, I think now we are stronger together that we both have full shells, Katie.
Exactly, and that's exactly what happens with atoms too. So in ionic bonds, that is what we looked at with sodium chloride. So one atom will actually give one of their electrons to another one atom, and then they're both going to have full shells, because that's the most important thing to atoms, is they want to have full shells. So if one has an extra electron, they're going to give it away. If one needs one more electron, it's going to be asking around like, hey, can I please borrow your electron? And that's why some of these chemicals will happen. Some atoms will go more together than others. So we can see in sodium chloride, it fits perfectly like a puzzle. One gives and one receives. But if there's other kind of atoms, some of them kind of have half full, or if they're already full, then they're not really wanting to give and receive. And so that's what an ionic bond is.
Yeah, exactly. I drew this little arrow here to represent that this electron that sodium has, like the extra one, it can actually be transported and donated to chloride to form an ionic bond. And pop quiz, Kat, NaCl. What is NaCl?
NaCl is actually table salt.
Yeah.
So Katie has NaCl with her right now.
Yes, exactly. And these transfer of electrons is the result. It results into static electricity, which is what we're all learning about today. And how do I measure or like see static electricity? I know that there's a device to measure all of that. What's it called again? Electrogram. Oh, right. And that is today's activity, and it's going to be a great one. So make sure that you download the lab manual so you can find all the materials that you will need and follow instructions. But we're going to do that today. And the materials that you will need are a glass jar, some aluminum foil, tape, cardboard, paper clip, pencil, and scissors. Right, Katie. All right, I'm really excited. I want to see how this electrogram is made in. So what's the first step on how to make this?
All right, so once you have your materials, let's go ahead and get started. We're going to build our electrogram, and what we're going to do is we're going to be able to measure and see which objects have static electricity. So we're going to go ahead and we're going to take our jar, and the first thing we're going to do is we're going to pop off this lid. You can keep the lid if you want, but we don't need it for this experiment. And what we're going to do is we're going to take a little piece of cardboard, and we're going to turn our jar upside down, and we're just going to trace a circle on this so that it's going to fit around our jar. Now, it's really important that our circle is going to be pretty much an exact fit, because this is an important part of our electrogram. And we're going to go ahead, and you can see that I kind of have a really nice circle there that's going to fit my jar perfectly. So once I have that, I'm just going to take some scissors and I'm going to cut so that's around the circle. Now, if it's not perfect, that's okay, but just try your best to make sure that you're cutting on the lines so that we can have a very nice fit to our jar. So as I'm doing this, we're going to go over to Kat and we're going to see what the next step is.
So once you have that nice circle cut out of your cardboard, you're going to put that to the side and you're going to grab your paper clip. And we want to take our paper clip and we are going to bend it so it's nice and straight as you can get it. And then once you have it pretty straight, you're actually going to take the bottom and you want to make kind of a J shape. So not too curved, but just enough that we can hang something on there, almost like a Christmas ornament.
Or like a hook.
Yeah, just like a hook. And Katie, what is next after we have our paper clip ready?
Okay, so now we have our paper clip. What we're going to do is we're going to take a smaller piece of aluminum foil and we are going to be cutting little kind of leaflets. So if you can imagine what a leaf looks like, that's kind of what we're going to be cutting in our aluminum foil. So I'm just going to go ahead and I'm just going to make a little bit of a line across. And then I'm going to kind of do a little bit of a curve up. So that kind of makes a point at the top. And then I'm going to do the same on the other side so that we have a little leaflet that kind of looks like this. So I'm going to go ahead and I am going to do the next one. So make sure you're cutting 2 of these and you want kind of a straight bottom and then kind of like a little curve at the top. And what these are going to do is these are going to actually measure if our item has static electricity. So now I have these 2. I'm going to go ahead and I'm just going to take my pencil and I'm just going to kind of make 2 kind of small holes right at the top. So it's kind of like a triangle and you want to make a very small hole at the top of our triangle. And now, there we go. You can kind of see that, our hole there. And now what we're going to do is we are going to take our paper clip and we are going to just thread our little leaflets through the paper clip. And you want to make sure that you're doing it on the side that is hooked. So remember in Cat's step, we kind of made this little loop. We want to make sure that we are threading it through this loop. And this is one of the most important things of our electrogram. We need to make sure that the leaflets are not touching. Okay, if they are touching, then our electrogram is not going to work. So you can see here on mine that they are not touching. And we need to make sure that we build ours the exact same way. So make sure they're both on kind of this U-shaped bottom, but they cannot be touching. So once we have that, Kat, what would be the next step?
So next you want to pick up your cutout piece of cardboard and we are going to punch our paper clip through the center of our cardboard.
So the opposite end of the paper clip.
Yes, the opposite end of the paper clip. We're going to punch this through very carefully.
Right. And if you can't get it, remember you can always ask for help, like an adult to help you out to make that hole.
Just like that. And then we are going to place our paper clip in our jar. Now here it is very important that the leaflets do not touch the inside of the jar.
Ooh.
And then we are going to secure the paper clip in the cardboard with some tape, and we're also going to secure the cardboard to the jar with some tape here. And one thing that I did forget to mention earlier with the paper clip is that you want to try and make sure that you're using a paper clip that doesn't have insulation on it. So that's maybe if you have like a red or blue or pink paper clip, you want to try and peel that plastic off. And that's because the insulation is going to stop the electricity from flowing through.
Oh, so insulators stop the flow of electricity. What's the opposite of an insulator again? A conductor. That means the paper clip, the metal part, is the conductor allowing electrons to flow through it, and a insulator is something that blocks it. Pretty much like the coating of the paper clip will block the flow of electrons. And how I like to think about it is like a pot of soup, right? If I'm stirring a pot of soup, do I want to use a wooden scooper or a metal scooper? Katie?
You want to use a wooden scooper.
Yes.
Yes.
Yes, I need to use the wooden scooper because the wooden scooper is an insulator. It blocks the flow of heat, right? It blocks flow of energy, and I won't burn my hand. But if I use a metal scooper, it's a good conductor, so that heat energy is going to flow through and burn my hand. It's going to hurt. So that's how I remember it. All right, Katie, what is it? Kat, what's the next? Oh, Katie, what's the next step?
Yes. All right. So we are almost done. We're on the last step, and I think that this is the most fun step. For some reason, crushing things into little balls is really fun. So I'm going to go ahead and we're going to take a little piece of aluminum foil, and we're just going to crush it up. And we want to crush it so that it's in kind of a small little ball formation, just like that. Perfect. So then what we're going to do is we're going to just kind of stick it on top of our paper clip here so that it kind of pierces through. Oh, my tape's coming undone. There we go. So that it pierces through. And that, ladies and gentlemen, is our electrogram. What do you think about that, Kobe?
Wow, that looks pretty good. And I'm kind of like sad because like I should have like followed along and brought my materials to build one. But since I am a magician, I will use my magical powers to replicate whatever I see. So 3, 2, 1. Bibbidi boppity boo! Wha-bam!
Wow.
I know. I'm so great.
Those amateur magician lessons are
Well,
really paying off.
You know what, Kat? If Kobe's so magic, then I think maybe we should go ahead and we should test to see if he is able to work this electrogram. So while he's getting that set up, how an electrogram works is what we're going to do is we're going to charge something with electricity. So to do that, you would have seen Kobe do this already. You kind of rub like a balloon against your head or against your shirt or a styrofoam plate, anything like that. And what we're going to do is we're going to bring those things closer up to this aluminum foil ball. So I see that Kobe's already doing the balloon. So if you're following along at home, make sure you're charging up whatever you're going to test. And then when he's ready, he is going to move it closer to the aluminum ball. And then if we could get a close shot up on that electrogram, we're going to be able to see those leaflets kind of move out.
And I remember that the leaflets have to be separate and not touching one another. All right.
Here we go.
Leaflets are not touching one another, and ooh,
Wow.
one more time.
Science.
Wow.
Ooh.
Okay, so when we're seeing that, we can actually see the leaflets move apart, so we know that that balloon is carrying charge. Should we test something else?
Yeah, I don't know. I don't think Kobe could make it work with a paper plate. What do you think, Katie?
Yeah,
Paper
no,
plate?
I don't
Or
think.
a styrofoam plate?
Yeah, let's try a styrofoam plate.
Yeah.
Okay, I don't have one. But I remember it from my memories. Ready? 3, 2, 1. Oh wow! A paper.
Wow.
Styrofoam plate. All right, let's try this again.
Katie, I think we should be paying for tickets to this magic show we're at right
I think
now.
so. You know what, Kat? I think that we should get VIP tickets because we're the one that are teaching. We're teaching him all his tricks.
Yeah, I want a cut of your sales.
A cut of my sales. Well, VIP tickets are actually twice as much, so they're gonna cost like $200. So you're gonna have to pay $200. All right, I think it's ready. Let's try this one more time
Here we go.
with the styrofoam plate.
Wow.
Ooh, let's try it again.
A little bit there.
Ooh, wow! Look at that.
Whoa. They're like flapping. Their little wings flapping.
Wings flapping. They're like mama butterflies. Flapping wings.
So we know that the styrofoam plate also holds a charge. So what if we did something that doesn't have a charge? Would it work the same? What do you think, Kobe?
If it doesn't have a charge, no. I think it really depends on the material. And if you have any questions during the episode, text in your questions at 306-570-1013. And if that doesn't fancy you, then you can reach us through our social media with the handle @EyesYouth. So Facebook, Twitter, Instagram. And remember to use that hashtag #CouchPotatoLab so we can find your questions. Thank you very much. And let's talk about what you meant, Katie. So different materials can actually like gain electrons or lose electrons, and based on what they're made of, some materials have a tendency to attract more electrons or donate more electrons. So let's take a look at a triboelectric series, and while you take a look, I'm going to explain how this works. Alright, as you can see, this triboelectric series is a list of materials, and at the very, very top are positively charged materials that are more likely to lose electrons. So that would be like rabbit fur, hair, glass, mica, and wool. And rabbit fur is more likely to lose electrons than wool. So wool, you would say, would be closer to a neutrally charged material. On the other hand, materials like Teflon or polyethylene, acrylic, polystyrene, rubber balloons, or styrofoam and stuff like that, they have a tendency to gain more electrons. And when they gain electrons, they are going to become more negatively charged. And a rabbit fur, for example, when they are losing electrons, they are going to be more positively charged because they are losing that electron. And remember that electrons are negatively charged, right? So the more you have, the more negative you are, and the less you have, the more positive you are. And whenever these two materials come in contact with one another, for example, like my hair and a balloon, right? A balloon will be more likely to lose electrons, becoming negatively charged, and my hair will become more positively charged, so it's more higher up on the triboelectric series, and this will be more lower down, ranking a little bit higher on losing electrons or becoming more negative.
So, Kobe, would that be something like, if we actually tried to do a paper plate with our electrogram, that would not work because paper is not conductive, and so that would be weird if we were like writing notes and then we got like electric shock. So paper would not be that, right? So it wouldn't work with a paper plate.
No, not really. I think like paper plates are more neutrally charged, so like you're not going to see that shock happen. So that means it's probably in the middle of that triboelectric series compared to like styrofoam plates, for example. And remember when Katie was doing her salt and pepper demo, she asked me to use a comb first, and that didn't work as well when I rubbed with the balloon. So that means this balloon is more negatively charged, or it has a greater tendency to gain more electrons than a plastic comb. Yeah, and materials and all that, it's great, and it creates static electricity. But do you think there is like static electricity naturally in our world? Katie, do you know much chance?
There most definitely is, and we actually saw an example of that last night. So you were probably getting ready for bed when you heard a huge thunderstorm rolling over. I know I did. My house was like shaking from the thunder. So during that thunderstorm, we have both thunder, lightning, and rain as well, usually. But lightning is an example of static electricity. So remember that this has to do with electrons jumping, and it can even cause a spark, exactly like that. So we have another thunderstorm right now.
Oh my goodness.
So we're going to go ahead, and we are actually going to make our own lightning. And no, it's not going to look as nice as that. But we're going to go ahead and give it a try. So you can go ahead and follow along with me at home if you would like. If not, you can watch me get shocked. So we're going to go ahead, and we are going to take an aluminum pie plate, and we are going to stick a pin through this pie plate, through the bottom of it. Then we're going to turn it over, and we are going to stick a pencil through this. So we're going to go, and we are going to just kind of stick it in. Ooh, hopefully it doesn't bend. There we go. So then we have kind of like a little bit of a handle for our aluminum pie plate. So the next thing we're going to do is we are going to take any sort of wool material. So Kat was lovely and she brought me her wool socks. But if you have any sort of wool material at home, then you can use that. And what we're going to do is we are going to just go ahead and we are going to rub the wool against the styrofoam plate. And we're going to do that just for a little bit a while. And what are we doing? We're collecting the charge when we're doing this, because remember that if we don't do this, then we're not going to have any sort of electrical charge. And so we need to generate that electrical charge with something that is actually capable of doing that.
Mm-hmm. Oh, and remember that wool on the triboelectric series is a little bit higher, so it's on that series on the list where it lose electrons. Right? It's going to become a little bit more positively charged. Thus, if that's the case, then the styrofoam would be more negatively charged and gain more electrons. So pretty much what's happening is that the electrons from that wool sock is going to be transferred to that styrofoam plate.
Exactly. So once we think it's nice and charged, we're going to go ahead, pick this up with the pencil, and we're just going to go and rest it on this plate here. So then if I go and I touch this, then I get a little bit of an electric shock. So it's not very harmful. It doesn't hurt that much. But if you want, you can try it at home too. And that's how we can even create our own lightning. If you want to go ahead and give it a try with the lights off, you may even be able to see a little bit of a spark. So we kind of created our own lightning, which is pretty cool. Hey, Kobe?
That is really, really cool. And maybe I can like shock the both of you. That could be part of my repertoire. Hey, that'd be cool. That'd be cool. And I know. So that's cool. Thunder, lightning, and all that. And thunder is the one that makes sounds, and lightning is the static electrical ones with the visuals. But are there any like instruments that use static electricity? Instruments mean like devices or anything like that?
Well, Kobe and Katie, have you ever looked around at your office supplies and wondered, where is static electricity taking place in here?
Cat, that keeps me up at night. All the time.
Well, you're going to have a wonderful night's sleep tonight, Katie, because photocopiers use static electricity. And we do have a wonderful graphic that we will pull up here. So as you can see, the drum is positively charged. So that's what that clear piece of the machine that you lay the paper on. And the ink is negatively charged. So when you photocopy something, those opposites attract and the ink particles are rolled onto the paper, and positively charged roller makes those ink toner particles fuse with the paper.
Oh, wow. That's cool. That's cool. Static electricity is also found in our office. That is dope. So that means our teachers who use photocopiers and photocopies all of our assignments is using static electricity every day. Crazy to think about that. Wow. Okay, now that we learned a lot about static electricity, I kind of want to test both of you. Yeah, because I think it is time, for the science showdown. Alright, so today's science showdown is what's going to happen is I'm going to show you a picture. And in this picture, you're going to identify what maybe uses static electricity or what is static electricity. You're going to buzz in your answer with your little buzzer. So maybe with your moo-moo buzzer or your cock-a-doo-doo buzzer.
Where's my cock-a-doo-doo buzzer?
Right there, right behind you.
Right here.
Yes, alright. Once you press your buzzer, then you may answer first. And then once you do that, the person who was a little bit slower can answer as well. And let's say the loser of this science showdown will have to do a dare. So the winner will dare the loser to do a funny dare. My favorite. I hope Katie loses. Okay, anyways. Alright, here is the very, very first picture. Ooh, okay, it's an office.
I forgot. Kobe.
Yes.
I already know this because Kat was just talking about it. It's the photocopier.
Yeah, photocopier. All right, Kat, what's your answer?
I was going to say photocopiers too. And Kobe, I was wondering, now that you know so much about photocopiers and they're so cool, are you going to include them in your magic show?
Yes, maybe what's going to happen is I'm going to put my hand on the photocopier and then produce mass, just mass pictures of my hand. And then that will be I'll have my autograph there and then use it as... merch. Merch, exactly.
There you go.
Yeah, the kids will love me. Wow.
Nobody will come.
Okay, Katie. You're just jealous. All right, and here is the next photo. Take a look. Ooh, that was fast.
Cat's cheating.
Okay, Kat. What's the static electricity?
So the static electricity is all that lightning shooting down from the clouds because there's so many electrons in the air.
Yeah, all right then. Okay, Katie, what's your answer?
I also have to agree. I think it is the lightning as well.
Wow, you guys are so smart. It is the lightning. Very, very good. Nicely done. So that's 2 points for both Kat and Katie. We're a little tied here. All right, here is the next one.
Get out of here!
All right, I think the static electricity is found within the slide because the little girl that was sliding down the slide has like really like frizzy hair.
Bonus points.
Okay.
She has the frizzy hair because when she slid down the slide, electrons were passed to her from the slide, and that's why her hair is going crazy.
Kat, there's no bonus points.
Yeah. Wow, Katie's getting a little scared here. She might lose. And the correct answer is the slide, right? So the electrons actually are passing through from the slide to the air and then to that little girl, transferring it to the hair, and it right? So the hair is positively charged, right? So all the electrons is actually flowing to the hair, causing a little frizzy hairdo.
Can I be honest? It took me a long time to figure out where the static electricity was in that.
Really?
Yes, I didn't notice the children first. I looked right past the children.
Maybe it's the sun.
Yeah.
All right, so that's 3 for 3. Wow, you guys are on a roll. Woo. Okay, number 4. Here is the next one. Here's a picture.
My buzzer's broken. My buzzer was broken for a second. Okay, I'm gonna say the door handle because I used to do this when I was little. I would like rub my socks on the floor and like touch like the light or something, and or like the door handle is also metal. So that's what I would say. I know Kat used to do that when she was younger too.
Yeah, I did that all the time, and my grandma would get so mad at me and so worried that. But I'd say, "Grandma, look, lightning!"
And you would shock her. Ooh.
No, I would just shock myself.
All right, and the correct answer is yes, it's the carpet and the doorknob. So here's a little picture of what is happening and how we are actually shocking ourselves. So what happens is that we are negatively charged, like our clothes and stuff like that, or our socks. And the carpet, on the other hand, is positively charged. So when we're walking or like, scraping our socks against the carpet, it's creating that electrical charge happening. We're becoming more more negative. And the door, on the other hand, is positively charged, and because opposites attract, touching that doorknob will cause a little reaction, a static electrical reaction. So very good. We're all tied up. What is going on? All right, here is the last question.
This is the last one?
The last one. Spot the thing that has static electricity behind your shelves. All right, there is something that deals or uses static electricity. Are you sure, Katie? You want to go first?
Yes, I do want to go first.
Okay.
I know that I'm not usually this competitive, but this is something that I have to do for myself right now. I am going to say that it is this wonderful contraption right here, and it's the plasma ball.
The plasma ball?
Yes.
All right. So
Are you sure it's not a polar ball?
Yes, I'm positive.
So Katie thinks it's the plasma ball. All right, Kat, what's your answer for this?
I'm scratching my head at this one. At first, I noticed the potatoes, and the potato is growing something from it.
See the eyes of the potatoes?
Maybe these are like it got hit by lightning, and now it's sprouting things from it. That's my guess. This Pepe, what's this potato's name again, Kobe?
Pele, Penilorium, Priyanka, Potato.
Stunning. Yeah, so this is my final answer.
All right, that's your answer. All right, and the correct answer is, drumroll please, is the plasma ball.
Oh,
Katie, you're
Thank
trash.
goodness.
So that means, Katie, you won today's Science Showdown. Nicely done. All right. If you got everything correct, make sure you text in your questions or your comments, or if you got it correct or not, at 306-570-1013, or you can always reach us through our social media with that handle at EyesYouth, like Facebook, Twitter, and Instagram, or TikTok, or YouTube. And if you're going to use any of that, make sure to use that hashtag CouchPotatoLab so we can find your pictures and diagrams and comments and questions. So thank you so much. All right, Katie, do you know why the plasma ball involves static electricity?
Yes,
You
I
do?
do.
Oh, really?
Slightly. I will give it my best shot, and then you can
If
correct
not,
me.
I'm gonna steal and I'm gonna win the whole thing. I got my buzzer right here. I'm ready.
So I know that it has to deal with the plasma ball being charged, and then it is transferring of electrons. And I know for certain that if you hold your hand over it for a long time and you hold a light bulb, that eventually that light bulb is actually going to light up because it is moving those electrons around. Covey, what do you think
Okay.
about that?
Yup. Kat, anything to add?
I was going to say that there's a pink jello in the center, and when you touch it, the jello just warms up and it melts and it touches your hand. Is that all right?
Sort of. So what happens here is that there's an electrode, right? So I think we mentioned that before. The electrode is causing like an alternation between positive and negative charges. It's moving towards the glass, and because the glass is more charged when we touch it, because we're kind of like positively charged. Yeah. So that's how static electricity works. And then if you like touch it long enough, your
Ooh,
hair might
Katie,
actually
touch
stand
it.
up.
Touch it, Katie.
Is it gonna shock me?
No. Now watch Katie's finger. Whoa.
Wow. Yeah, look at that. Static electricity. It's all static electricity. Wow, it's been here for like so many episodes, but we never explained it. So here, this is perfect time. All right, and because Katie won the science showdown, you get to dare Kat to do a dare. What have you decided on?
You know what, Kat? That is, we're not gonna do the balloons. I was thinking maybe we could do something balloons, but I hate balloons, so we're not gonna do that. I would love to see your best static electricity dance.
Okay. I do this all the time. When I'm home alone and I can't fall asleep at night, I just start making dances for static electricity. So first, you gotta like shoot the static electricity. So you're gonna go, and then bring it back, and then overhead, and then you have to fire it off to your friends. Ready, Kobe? It's your turn.
Good passing it to you, Katie.
And we were getting rid of it.
All right, thank you so much. Now I've learned a lot about static electricity. I can include it into my magician repertoire. And I think it's time. Why don't we do one more little trick? Because I want to showcase my static electricity magic as well. And I think, Katie, you have something cool to show us,
Yeah, I
right?
mean, I thought that maybe what we could do in preparation for Covey's magic show is that we could go ahead and we could have a little bit of a talent show between the three of us. So I'm just going to go ahead, and my talent show is actually going to happen near a sink. So I just have to go off and head to the sink, and I'm going to bring you guys along with me. So let me come with me, and I'm just going to go off to the sink now, okay? So let's go.
All right, bye, Katie.
I'll be there in a second.
Oh my God, Katie, hurry up.
Katie.
Sorry, it takes me a long time to get there. Oh, okay, there we go. All right,
wow.
so you can see that when I'm bringing this balloon closer to the water, that the water is actually bending towards the balloon. And what's happening there is that the balloon and the water have different charges. So I can actually have the ability to move water. So it's pretty cool, and I'm back. So there we go.
That was fast. You're super speedy.
I know. That's my portion of the talent show. I would like to see what Kat has because we have a very love-hate relationship today. So I would like to see what she has in store.
Well, because I know that Katie loves balloons so much, that's why she included it in hers. I'm also going to include it in mine, but I'm going to one-up her, and I've made oobleck. Yes. Oobleck. So oobleck is really cool because it acts as a solid and a liquid. And Kobe, do you remember what the term is to describe oobleck?
Yeah, non-Newtonian fluid.
A non-Newtonian fluid. So if I hit it, Here, I'll bring it over here. So if I hit it, it's like a solid. But if I get my fingers in it, and it kind of melts in my hand.
Oh, yeah, right. Oh, right. Applying force it will act like a solid, but without the force, it will act like a liquid.
And so we're going to do a similar experience as Katie's, but better, because this is a talent show, and I'm trying to win.
Okay.
So, Kobe, I am going to enlist the help of you because you're such a talented magician. I know you started out as a magician's assistant, and now it's your time to shine once again. So, I am going to ask that Kobe is charging up this balloon right now, getting all those electrons passed into the balloon, and I'm going to run my oobleck stream down and we'll see what happens. It will run.
Will it? I think it's a little too solid here.
Should I add some water?
Yeah, maybe a little.
Okay. Let me just run to the sink as well and I will add some water.
Or a water bottle. Here, use mine. Oh, that's a lot of water.
Oh, I don't know how this talent show's gonna be. You guys are kind of off to a rocky start here.
Are you ready, Kat?
Yes, I think we're ready.
Okay.
It's a little bit watery, but okay. This should work. Ready? Balloon is charged. Oh!
It's like somewhat. Ooh! It's bending.
Wow, you
That's
know
cool.
what? I guess that's pretty cool, Kat.
Thank you.
You're a pretty cool cat.
I guess, Katie, I guess yours was pretty cool too.
Wow. Now the only thing left we have is whose.
Yeah.
Oh, me, right. Yeah, that's cool. All right. Our favorite segment, Ask Our Scientist, is coming up next, where we're going to answer your questions. So before we do that, we're going to do my little magic trick. All right. So what I have here is a cup and a piece pencil. Lols, I forgot my words. I stuck it through it, so it kind of acts like a pencil holder. I have a piece of paper. I'm going to put it on top of the pencil right here. And I, with my static electricity, will move the paper. Ready, set, go. Ooh.
Wow, Kobe.
Other way. Oh, I'm still moving. Ooh. I'm not touching it. Look at me go.
Wow, that's pretty cool. You know what, Kat? I think overall that he's ready.
I think, I think through this episode we've really learned that Kobe, I guess, might have what it takes to make it out there on the hard ways of a magician out. He might be able to do it.
I'll be able to do it. Thank you so much for all those demos, because that would be really cool. And now it is time for our favorite segment, Ask Our Scientist. All right, and our very, very first question comes from the Hayes brothers. What is the best way to not be hit by lightning? Ooh, that's a very good question. Katie, do you have the answer to that?
Good question. Yes. So when we are looking at lightning, the most important thing is that we are staying safe. So what we want to do is we want to actually get inside. If you're inside, that's the safest where you can be. If you're not able to get inside, then we want to try to remain low to the ground, because if we are up high, that's usually where lightning strikes, is somewhere really high. So if you are outside, try to remain low, but if you can, try to get inside.
Awesome. Thank you so much, Katie. Next one comes from Eli. What rocks have magnetic forces? Ooh. Good question. Okay, Kat?
So a lot of different rocks are naturally magnetic, and a great example of one is magnetite. And magnetite will actually stick to the front of your fridge without any help. So that makes you wonder, hey, I wonder how did it get its name? But there are other rocks too that aren't magnets but are magnetic. So these rocks have a lot of iron in them. And so while these ones won't stick to your fridge, they will stick to a magnet.
Oh, ooh, I remember when we did our rock episode, we had a rock called magnetite, and it actually like attached to the magnet. So that was cool. All right, Katie, the next question is from Eli again. How does gravity work?
Good question. Okay, so gravity is another type of force, but it's not the type of forces that we were looking at today, like magnet forces. We're looking at protons and electrons. Gravity does not use that, but gravity rather uses mass. So on Earth, we are able to be held to the Earth from its gravity because we are drawn to it. It's due to our mass. So luckily, with this type of gravitational force, we're able to stick on the ground, but we're still able to kind of move freely. However, gravity is actually one of the weakest fundamental forces. So do you remember when I did that salt and pepper demo? You could see that even though gravity was pulling down the salt and pepper, the pepper was actually jumping up to the balloon. That's because that type of force is stronger than gravitational force.
Oh, really? That's cool. I didn't know that. All right, next question comes is what bond is stronger, ionic or covalent? Kat?
Great question. So scientists have found that covalent bonds, those bonds that share electrons, seem to be weaker than ionic bonds, the bonds that steal an electron from another atom. Or molecule, pardon me. And this is because ionic bonds form a lattice structure, so it's really strong compared to a covalent bond.
I see. All right, last question, thank you, Kat, is in what kind of things do we find sodium chloride from the Hayes brothers? Ooh, easy question.
Good question, Hayes brothers. So we basically find it in almost all of our food. So table salt, bread, soup, cheese, anything like that. Mostly all of our foods have salt.
And in our bodies as well. That's why we can conduct electricity. Ooh. All right, thank you so much for joining us and helping me become a cool static electricity magician. If you want to try out these demos, you can, and they're really, really easy to simple. Just follow along and like watch some of them again. Thank you again for watching. All we got to say is bye. Thank you so much.
Bye, everybody.
See you next time.